Hello. All right, let us wrap up chapter 9. Should be brief, actually. And then we will move on to chapter 10 next lecture, which starts us on rotation. So today we are talking about the center of mass. So we're continuing our discussion of how to understand physics when there are multiple particles in the system. Up until we were considering momentum, really we were always treating everything as just a single, what really is called a point particle. I talked about apples falling from the sky. I was not actually ever considering the fact that this apple has some extended shape, right? It's not just literally a point that is falling from the sky. And looking at this pen, the pen, I could drop it and it would still fall at 9.8 meters per second squared. But it clearly is not the same as the apple in the sense that it has a very different shape. It is made up of many, many, many atoms and molecules that give it some sort of structure that in this case is very elongated versus something which is closer to spherical. So the question we get asked is, why was I okay with that? Why did no one immediately riot with the idea that I did not have to do, say, Newton's second law for every single molecule that makes up this apple? Why could I just take the total mass of the apple, or the sum of all the atoms and molecules in the apple, and treat it like a single point that fell at 9.8 meters per second squared? Even though there are so many other forces in the problem. The fact that this is a solid is because there are chemical bonds, which are forces, essentially a bunch of tiny little springs as the electrons are being shared with all the atoms and molecules, and they form a sort of a molecular structure that holds the apple as a single solid shape. Why are those forces not coming into play? Give an example of what we're talking about. I have the apple, which is my system. But if I zoom in on that system, that apple is made up of many, many, many individual objects. The atoms and molecules and the electrons and whatnot that make up the apple. If I were to zoom in on those individual atoms individually, there's forces going on inside the atoms. There's electrons and there's protons and there's neutrons, and there are various forces that are acting in between all of them. Why is this not coming into play why did we not have to include any of that when I dropped an apple and claimed it fell at 9.8 meters per second squared? And the gravitational force was something like 9.8 meters per second squared multiplied by the mass of the entire apple. Now, and of course, we could have done this analysis by doing F equals ma for every single individual atom and molecule that makes up this apple. We would have gotten the same answer. And so why is that the case again? That comes down to Newton's third law. If this is my system, the entire apple, and I'm asking, how does the system as a whole accelerate? What is the net acceleration of the entire system? We've now talked about this, that the acceleration or the net force on the entire system, or in this case, F net external to the system, equals to the change in total momentum of the system. It's telling us how the system's momentum is changing, how the velocity of the entire system is changing, perhaps in magnitude and in direction. And we never had to consider all those internal forces, because since all those internal forces are inside the system, for every tug between the molecules of the apple that points this way, there's another tug that points in the opposite direction. For these two particles, there's a tug this way and there's a tug this way. There's no net force when you consider all the internal forces inside the system, because all of those internal interactions have a Newton third law force companion. So it's only the external forces that matter as to how the entire system accelerates. Or the way I'm saying it here, change momentum. Remember, we wrote Newton's second law. Just to remind, Newton's second law, a way we wrote that was that the change in momentum as a function of time is equal to the net force. That was a statement of Newton's second law for an individual particle. And then we saw for a system that is composed of many particles, we could write it like this, where it is the net force on the entire system that changes the momentum of the entire system. If there's no net external force, then momentum is conserved. So if we suppose that this entire object remains, nothing enters or leaves the system, I could ask myself, okay, there's some net external force on this entire system, which again is the change in the overall momentum of the system, which is the same thing as the change in the sum of the individual momentums for every particle that makes up the system. And overall, the only way that can change overall is through external forces. Let's study the entire system as a whole. Let's take the entire system to have some overall acceleration. So we'll say we'll have acceleration, I'll write capital A. So this is the acceleration of the entire system, right? What makes up the entire system, all the individual molecules in this case. It might be, the entire system might be the entire solar system if we say that there's nothing else but the solar system. But maybe some, one distant star pulling on the entire solar system. The entire solar system might then have its momentum will ultimately change. The change in momentum relates to forces, which relates to accelerations. We can ask then ourselves, what is the entire system doing in terms of acceleration? Well, in that case, so ultimately what we want to say is we want to write F net external equals m of the system times A, big A of the system. The mass of the entire system times the acceleration of the entire system, we're going to relate that to the net external force that's acting on the system. So essentially, again, the idea is we're treating the entire system like a single unit. I almost said solid unit. It doesn't necessarily even have to be solid. For example, the solar system, right? The individual things inside the solar system are moving around, but as long as they're not entering or leaving the system, that's fine. We're just asking as a whole, as the Earth goes around the sun, does its thing, what does the solar system do as a whole? What does the apple do as a whole? Well, we can write this down just simply by our statement of how momentum changes. F net external equals the sum of all the individual momentums that make up the system. Rather, it's how that is changing with time. Move this over a little bit. Which I'm going to want to write as m, and instead of m system, I'm going to write mt for m total. That's the same. Times A of the system. So in this case, what we're saying is m total, A system, equals the sum, or rather the change in all the individual momentums of the particles that make up the system. Which in this case, I'll write it as, the sum of m times v of all the individual little particles. I might put a subscript I to mean I add up all the individual molecules of the apple. I add up all the planets of the solar system. Which could even go further. I then could add up each individual, atom and molecule that makes up the planets of the solar system. I'm adding up all the individual components that comprise the entire thing. I'm going to start by moving the derivative, or rather the denominator of the derivative, to the other side. Easy enough. I had that dt in the denominator. I shift it over. I can then identify this, an acceleration over a tiny bit of time, a times delta t. We've seen that before. The acceleration is defined as dv dt. Now I have acceleration times dt. This is, of course, nothing other than, we could write this as v in this case. Let me walk slower through that. I skipped a couple steps admittedly by doing that. The change in velocity as a function of time, dv dt, is defined as acceleration. We said that before, right? How the entire system's velocity is changing as a function of time, we would call that the acceleration of the entire system. And this is, we're going to distinguish that as a capital V, for V of the system, the entire apple, for example. And so by that case of what I wrote down, it's not just V, rather, I should have wrote down D capital V equals D, sum of all of these individual momentums. The acceleration times a little bit of change in time gives me how my velocity has slightly changed. That's chapter 2 or 3 or whatever it was. But now I can add up all those changes. How does the bulk change occur when the apple falls from a large height all the way down to the bottom over a large period of time, not one little picosecond of time? How does it change in bulk overall? So adding up all the little things, that of course is the integral. So now I'm taking the total mass of the system multiplied by all of these tiny little dv's. But if we assume if the mass of the system does not change, then of course that can come out of the integral. This is just simply right, something like that. And the integral of just dv then is what I wrote down before. Then that is just v. And then the integral and the derivative on the right-hand side cancel out. The integral is the antiderivative of, right, the integral can be thought of as the antiderivative. So if I take the integral of a derivative, they cancel each other out. So this then just becomes the sum of the individual momentums. This allows me to define a velocity of the system, which is the sum of the individual momentums divided by the total mass. So I could also think of that as the sum of all the individual masses. So it might be mi vi divided by m total. So a mathematics course might also call this a weighted average. You're weighting each individual molecule that makes up this apple has an individual little mass, which is lowercase m in this case. And then the total mass of the entire thing is capital M. What you're doing is you're weighting each individual little velocity of each individual particle that makes up the apple, the little v's on the right-hand side. You're multiplying it, you're weighting it by its mass, but you're ultimately dividing by the total mass in the system. This is a weighted average. So you can think of this as that the velocity of the system is a weighted average of all the individual velocities that make up the system. That's worth a highlight. This velocity, v, is called the center of mass velocity. What this is saying is if there is a net external force on the system, like gravity pulling down on the entire apple, then in that case, the entire system starts to move with some velocity. What that velocity is depends on the external acceleration, right? The F net external results in an overall acceleration, which says how the entire system as a whole starts to move. That velocity we call the center of mass velocity. And no need to stop there. We just said that m total is v of the system equals the sum of the individual masses times the individual velocities. But velocity is the derivative of position is velocity. So I could also write this as m total dr of the system dt equals the sum of the individual masses times dr of the individual masses that make up the system dt. There is a dt in the denominator on both sides. I could get rid of that. This then results in saying that the mass of the entire system times its change in position is the result of the sum of the individual masses times all their individual little changes in position. The next step then, of course, I see all these tiny little incremental elements. I could ask, how does the system overall change position? So I add up all those small changes. That gets us something like mt big R equals the sum of m. All the little m's are constants, so the integral on the right-hand side just becomes big M or little m times the individual positions of each element. Maybe we can write this down. Individual mass times position of each particle in the system. Tell me the position and the mass of every atom and molecule that makes up that apple, and I'll compute that sum. This is then the total mass. This we then define as the center of mass. Or I could write this down another way so that I can give it a highlight. The center of mass position is the sum of all the individual positions weighted by the mass divided by the sum of the masses, or MI over M total. Also worth a highlight. This is saying what the position of the entire system is doing. Calculate what is the center of mass of the entire system that makes up this apple. And then if there are net external forces, that overall center of mass, the position of the entire system moves with some velocity equal to the velocity of the center of mass velocity. And that center of mass velocity was changing as a result of a net external force acting on the system. This is the idea why, when I drop this apple, I don't have to consider the forces that are acting on each individual atom and molecule that make up this apple. What I can do instead is I can identify that my system is the apple itself. There are tons and tons of individual interactions going on inside the system, but by Newton's third law, those all cancel out and go away. And then all I have to care about in terms of how the entire apple moves as a whole is I have to ask, what is the net external force acting on the system? I can then quantify how the overall position of the apple changes. That position I could call the center of mass position of the apple. That center of mass position changes because the center of mass velocity changes in the system. And so that justifies the point particle approximation. the fact that I was able to drop this and say the entire thing fell at 9.8 meters per second with a mass equal to the total mass of the apple was from this exact relation. Ugh. Right, by saying m total r center of mass equals the sum of the individual masses times the individual positions, this allows us to analyze a system as if it were only a single particle with a mass m total located at the center of mass, located at the position r center of mass. The system as a whole changes because of external forces. In the case of the apple, all of the internal forces, all the interactions, keep the apple as a solid object, so the apple does not also change shape as it's moving around. In the case of, say, the solar system, where you have planets orbiting around, and then if I define my system as the solar system itself, but then there's some distant star over here that is exerting some external force. While the individual planets and moons and whatnot continue to move around in the system, that entire thing as a whole starts to move because of that external force. Everything within the system also starts to gain an overall additional momentum, really, pointing towards the right because of this pull towards the right. Though the moons and the planets obviously continue doing their orbit. Sometimes they're moving left, sometimes they're moving right, but overall the system starts to shift. To help your intuition, we will see this also when we do equilibrium. When gravity is uniform, like near the surface of the Earth, the center of mass is sometimes called the center of gravity. I.e. the balancing point. Balancing point. If you're in a uniform gravitational field, like when you're near the surface of the Earth, a good way to find the center of mass is to find the point where it balances and does not fall off your finger, say. So in that case, since I can do this, that means the center of mass is located somewhere here. If I put my finger over here, I won't do it, but obviously then the pen falls off my finger. The center of mass is not right above the balancing point. For an extended object, in this case it's kind of, this might be one-dimensional. This is two-dimensional. It has both length and width. Since it's essentially uniform, I might say that the balancing point is somewhere in the center. If I were to put my finger somewhere in the center of the box, and that would allow me to find, actually not. It's because it's not uniform. There's a laser pointer inside, so it's slightly off. So let me take that out. All right, so in this case, I can put my finger slightly in the center. I'll try to only put it at the center. It's a little precarious. But I think you get the idea. Right, there we go. All right, so my finger is right about here on the other side, which is roughly in the center. The center of mass is the balancing point when you're in a uniform gravitational field. I guess an easier example I could have used was your phone. The inside of your phone is essentially uniform. So as a result, when you put your finger in the center, it remains balanced. That would not be the case for, say, do I have something? Yeah. Like a tennis racket or a squash racket. In this case, the mass is extended in an uneven way. The racket itself, it's mostly cord, it's light. You have this heavier end at the side. So when I put my finger directly in the center of the system, instead what happens is the thing just plops over. Instead, there's more mass located in this handle than there is up here. So I have to put my finger closer to not quite at the center, but shifted a little bit over towards the handle of the racket. But still roughly, it was located about right here, still roughly in the center between top to bottom, but shifted a little off-center towards the heavier side here versus over here. Symmetry can be very helpful in that case, if you think of it as the balancing point. You're putting your point kind of where all the mass averages out to. And then again, to recap what we're talking about here, then if I locate the center of mass, I can throw the object, and that object moves as if the entire thing were located at that center of mass. So an idea here, an example that's a little bit more obvious is the one on the left. A baseball player throws a ball. The ball acts, it's essentially already a ball, a point. We could calculate the center of mass of the ball. It would be located right at the center of the ball. If it's a uniform ball. Then when the person throws the ball, chapter 4, projectiles, the ball operates, as a nice projectile that moves through as a parabola. It comes up and then comes down. As opposed to the person on the right who throws a bat, which is a little bit more oddly shaped. It's not perfectly shaped like a circle or a ball. But this person could throw the object and it would move through the sky in some way. It could even perhaps be rotating like it appears in this picture. But nonetheless, it would move if you were to locate the center of mass and put a big red light right where the center of mass of the bat was located. No matter what the bat was doing, it could be rotating, you could give it a little bit of spin. When you throw the bat, the center of mass acts as if it's a point, and the entire bat moves like a projectile. And the center of mass traces out the same sort of parabola, even though the bat itself might be moving around. There'll be parts of the bat that might be spinning or flipping, but the center of mass of the bat still moves like in a perfect parabola. And you can do this kind of with a baton. It's kind of the easiest thing to see. If you throw a baton into the air, it might spin around, but it nonetheless comes up and comes down. If you were to find the center of mass, which in that case would probably be closer to the center of mass would come up and come down at the same, and get the same answer as if you took the mass of the entire baton, turned it into a ball, and then threw the ball in the exact same way. So let's do a couple examples, and then we are actually done with this lecture. All right, so I guess the takeaway, if I had to say what is the takeaway, is that the motion of the entire system I guess from external forces moves as if the object is a point at the center of mass. This is for an upper level mechanics class, but you can actually show that you can write any motion you see, show me something moving. I can break it into two parts. The center of mass part, and then the internal rotation part, or the internal motions part. For example, the solar system. The solar system is moving around the center of the Milky Way once every couple 100 million years. while nonetheless the Earth keeps going around the sun once a year. So all of those, there is an internal motion part, the Earth orbiting around the sun, all the while the entire thing is moving around the center of the Milky Way. All right, how about the baton? Nice, kind of gets our intuition, or we can answer via intuition, but then also show the math gives us the same answer. Suppose I have a baton. It has some length L, and on either end of the baton is some ball with mass m, and let's assume the rod itself is fairly light. We don't need to consider the mass of the rod itself, just the two balls at the end. What is the center of mass of the baton? In that case, you might think from intuition, where is the balancing point? Where do I put my finger if I want to balance the baton on my finger? I might put it directly in the center, in between the two balls. So let's actually see how that works out. Notice I've laid down a coordinate system because we're dealing with vectors, so I have to specify coordinate systems. In this case, I put my baton such that I drew the coordinate system such that the origin went through one of the masses. So then our center of mass is the sum of the individual masses times their individual positions divided by the sum of the two masses. So this would be mass 1 R1 plus mass 2 R2 divided by mass 1 plus mass 1 plus mass 2. Given how I drew this, the position maybe I should put some symbols here. Let's call this 1, let's call this 2. So the left ball is located at the origin, so if I were to ask what is the vector that specifies the position of that particle, I would just say it's 0. So I'd say this is m times 0, and then this is m times L. Since this is really just a 1D problem, I could, I guess, do this as a vector where it's, L comma 0. The position of the second ball is located at a distance L from the origin to the right, and it's not vertical or at all. Divided by, in this case, 2m, since the masses are the same. And I guess this is 0 comma 0, of course, if we're thinking of this as vectors. So I know how to add those up. M times 0 plus m times L is ml, and m times 0 plus m times 0 is 0, divided by 2m. I know how to deal with scalars and vectors, so I would say our center of mass equals the vector L over 2, comma 0. The m's cancel, then you get L over 2. The location of the center of mass is indeed horizontally located L over 2 to the right, and it's not vertical in any way. It is halfway. So in that case, based on the picture, it is halfway in between the two objects. This is more review, but did you have to put the baton at the origin? No. And we didn't even have to put it along an axis. Suppose the baton was located over here. Here's the baton, like that. And perhaps the position of M1, where M1 is located at R1 equals, and maybe this is, I don't know, maybe it's 3 meters in the horizontal direction, and then 1 meter in the vertical direction. So this would be 3, this would be 1. Then the mass 2 is located at position, it would be at 3 plus L, comma 1. It's a distance L to the right of 3, but then it hasn't moved up or down, so the vertical component is still, of course, just 1. So in that case, the center of mass is what? In that case, then it is m times the position of the first object, 3 plus 1, plus m times the position of the second object, 3 plus l, comma 1, all divided by 2m. So let's see, if I look at the horizontal components, it looks like I get 3m plus 3m plus m times l. Then if I look at the vertical component, it looks like I get m plus m. I'll divide by 2m. Simplify that. 3m plus 3m is 6m plus ml, comma 2m. Divide by 2m. If I divide the 2's in, I get something that looks like 6 divided by 2 is 3, so I get 3 plus L over 2, comma 1. So where is it located? Going back up to our drawing, I'll do it in green. It's located at a position I start, I go 3 to the right, and then I go L plus 2 to the right. So it looks like I go somewhere here. And then I go up 1. So again, the center of mass is located in between the two objects. If we had 3 objects, and maybe I have 3 particles located, and maybe this is at 2, 1, this is at 3, 3, and this is at 1, 3. And I could ask, and they're all, let's say they're all 1 kilogram. I could ask, what is the center of mass of these 3 particles? You could imagine maybe they're connected by very light, thin wires that keeps them as a rigid object, though that's not required. But in this current configuration, where would I put my finger if I wanted to balance all of this? This is the sum of the masses times the positions, divided by the sums of the masses. The denominator is 3 kilograms. 1 plus 1 plus 1. And then since the mass is just 1 kilogram, this is really just the sum of the vectors themselves. So all the x components, all the y components. So it looks like it could be 1 plus 3 plus 2, all the x components, and then 3 plus 1. So that simplifies 3, 5, 6, and then 3, 6, 7. I'll divide by 3. Looks like in this case it is 2, comma, then 2 1/3 meters. So if I go back to my drawing and see, okay, it's about 2, so it's out here, and then I go 1, 2, 3. I go not up just 2, but a little bit above 2, so maybe somewhere like right here would be the location of the center of mass. If this were, a Dorito chip, that was just 3 balls, that's where I could put my finger. Speaking of which, let's take that Dorito chip. But instead of thinking of it as 3 individual balls, what do I do when it's a uniform distribution of mass? So there's thousands upon thousands of individual particles that make up this single chip. So this for a uniform distribution of mass. So I don't just have individual particles or a small number of individual particles anymore. Now I have potentially trillions of individual little particles, all smoothly arranged in this kind of triangular shape. What do I do then? the formula does not change. I could still say the center of mass of this chip is the sum of all these individual tiny little particles times their position, plus the sum, or divided by the sum of all their tiny individual masses. But each of these individual masses, right, there's this one, there's this one, there's this one, this one, this one, this one. All of these individual masses are very, 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 very small. You know, it could be, I could be looking at the individual atoms or molecules that make up the chip, for example. And then each of them, let me do it in green and see if that comes out. Each of these individually have some position, right? Each of those individual little pieces have some defined position. Each tiny mass has a defined position. So each of these masses are so tiny, and the goal is we have to add all of them up individually. That's not too bad. That's the denominator of this expression. You know, this is just, again, m total of the chip. You know, take all of those tiny little masses, add them all up. Which, of course, to motivate where we're going with this, you can also think, of course, as the integral is a fancy word for sum. If you have trillions and trillions of tiny little masses dm, I could add them all up. That is what I mean when I say I do an integral. In the case of the numerator, what I'm doing is I'm adding up all of these masses weighted by their given position. Each individual little dm has its own position. I multiply them together, and then I add all of those up. So this actually gets us to the integral version for the center of mass. You can define it as 1 divided by m total times the integral of position times dm. Similarly, the velocity of the center of mass you can define as 1 over m total times the velocity times each individual mass. You can go back to where we wrote down the center of mass velocity and convince yourself of that. So if you ever have to do this as an integral form, you can break it up into a bunch of tiny little mass elements and add up each of those individual mass elements. For example, again, let's do one where our intuition is already set. Suppose I have a uniform rod. Or it doesn't have to be a rod, we could take the Apple Pencil, right? We can assume it's essentially uniform throughout. It's not heavier over here than it is over here. It's essentially uniform everywhere. It has some length L. And we could ask, what is the center of mass of this rod? Where m total equals, right, maybe it's some value m, big M. How might you evaluate this integral here? M total, of course, is just the total mass of the system. How much total mass makes up this pencil? Or rod, or whatever. The numerator is a little trickier, which requires us to remind ourselves about what we mean by density. So when we say a uniform rod, what we mean is that it has a uniform mass density. Or what's density again? Density tells you how the mass is distributed. it can be defined as, say, rho as the mass over the volume of an object. That is the definition of density, mass over volume. Which could be a function, right? If this were something where the density of the object changed from one side to the other, then the density itself could be a function of location. It's telling you if I zoom in on a little volume of this pencil, and I guess how much is in that volume, that gives me a sense of the density at that location. But the actual value for the density could change as I go to different locations. So this is right. It's mass. And really, it's over kind of spatial extent. So volume for 3D is the one we're probably most familiar with. It could also be surface area for 2D. I have a very thin, flat piece of paper. I could talk about the surface density of the paper, saying how much paper is there if I were to draw little squares on the surface of the paper. How much mass is located in each one of those squares. I'm essentially taking that third dimension to be so small that I don't need to worry about it. Right? Or the length density for 1D. How much mass is located at this little point compared to this little point compared to this little point compared to this little point. I'm treating everything essentially as a one-dimensional line. So again, mass per volume for 3D, mass per area for 2D, mass per length for 1D. You will definitely see this in Physics 3, where you'll have to actually do these integrals over surfaces and lengths. But for now, let's stick to 1D and what we mean by uniform. If uniform, that implies that the density is a constant. The object does not become more concentrated in mass here compared to over here, for example. The Earth is not uniformly a uniform density. The density at the surface of the Earth is much lower than the density at the core of the Earth. Things are packed more tightly together in the core of the Earth compared to near the surface. The density in the center of the sun is the reason why, it's one of the reasons rather, why the stars work at all. The density is so high, there's so much stuff in such a small space that nuclear reactions can take place. That cannot take place in, say, this room. The density is not nearly high enough. So if rho is a constant, that means m over... I have to think. In this case, we're talking about the rod. The rod is a 1D object, so I would say the mass over the length is a constant. Right? The total mass divided by the total length gives me the uniform average density. If it's actually uniform, then that's the true density. That is the same as if I only looked at, say, the left half of the rod, which would be over L over 2. If I just looked at this amount of mass, there would only be half the mass, but it'd only be half the length. So the 1D density, m over 2 divided by L over 2, would still be the same. I could also look, over a tenth of the length. From L over 10, there's 1/10 of the mass as well. The density, the ratio is still the same. I can shrink it more, 100th, a billionth, a billionth. So also this says that I can write this as dm dl in this case, where I'll say dx, since this is 1D. The density, if the density is a constant, I can write something like this. The density then is a little bit of change in mass over the change in length is the same no matter where I look along the pencil. If the surface density were a constant, that means I could draw little squares anywhere on the surface, and there would be the same amount of mass in each of those squares. A constant volume density means I could have tiny little cubes that I could fill with whatever my volume is. Maybe it's water, right? Anywhere I look, the same amount of water is in each cube. That is what we mean when we say the density is constant. Again, to use the Earth as the example, if I took that same, or maybe this is my little bucket, and I fill this little bucket with a certain amount of material, the bucket would have much more stuff inside of it at the center of the Earth, where the density is much higher, compared to if this thing were hollow and just filled with air here on the surface. The density is much lower up here at the surface compared to in the center of the Earth. More mass is concentrated into smaller volumes. So then back to the rod. The R center of mass of the rod is 1 over m total of the rod. Actually, let's do both integrals just to show. So this is the integral of, really it's x dm, because it's just 1d, divided by the integral of dm. Add up all the masses, that's the denominator. Add up the positions times the little masses, that's the numerator. But this also shows that we can do a coordinate transition. Or what is it called? A substitution. Yeah, that's what it's called in calc. A substitution to turn those dm's into something I can integrate over, because I have this x in the numerator that I don't really know what to do with. Because it's not a constant, but also it's not mass. So I could write this as x rho dx, and then this just becomes rho dx. So if you haven't gotten to this yet in Calc 1, what I'm doing here is I'm turning the integral into an integral over a different coordinate. Rather than adding up all the masses, I'm now saying look at each position along the rod and add up the position times the density. This is just rho times L in the numerator, denominator rather. And then this is rho L squared over 2 in the numerator. And you can look at your integral cheat sheet to help you out there. And then what happens? The rho's cancel, the L's cancel. This just becomes L over 2. The center of mass is located halfway along the rod. Perhaps not too surprising. You will see much more of this in Calc 3. We won't, really at this point, I can't really assume that we are all super confident with substitutions with integrals, but you will see it in Physics 3. And we will do some more of these. When we do moments of inertia, we will do a little bit of this as well. All right, I think that's it really for the numerical examples. But again, we could look at the, really what I want you to take away from this is to get your intuition about what it means to be the center of mass, and that if you can take away that for extended objects, that means when there's an external force on the entire extended object, the entire object acts as a single particle that moves. And its position is given by the center of mass. How that center of mass is moving is given by its velocity of the center of mass. Right, so I could ask a couple questions here, thinking now again about extended objects. A square piece of wood has a corner piece removed. The center of mass of the wood is in which quadrant? So before the piece was removed, I would assume that everything was kind of symmetric. The center of mass would have been right in the center of the piece of wood, located right here. But now I've taken this chunk out of the upper left. Where has the center of mass relocated to? In this case, I would say the center of mass is located in the lower right in this case. More mass is concentrated towards the lower right. That is where I'd have to put my finger in order to balance everything out, because all of this mass is now gone. If I kept my finger at the center, there's less mass over here than there is over here. So likely the object would tip towards where there's more mass. Depends on how fat my finger is. Same idea. So in the upper right, that chunk was removed again, so I would expect, just because of this chunk being removed, the center of mass would shift a little bit into the lower right quadrant. However, now this chunk was also removed. So I would expect, that it would shift it also towards the lower left. And since it appears like more was removed from this chunk than from this chunk, I would say that the center of mass is now located in the lower left. Again, looking at where the tipping point is, where the balancing point would be, if you were to try to take this plank of wood and put your finger where it needs to balance. In this case, I might put my finger maybe like here or something like that. All right, good. With these extended objects, these ideas of extended objects, we get into rotation, which will involve objects potentially rotating around other objects or extended objects rotating in space. Going back to the baton, like if you were to spin a baton, spin a Blu-ray disc. These are all examples of extended objects rotating, which will be important.